Hello, this is Professor Teresa Pelkie. This is Session 14, Part 3, Keys and Indexes. In this session, we'll go over some of the concepts of keys and indexes. You've already heard about the primary key earlier in this course. As suggested by the name primary, a primary key is the most important key for a table. The purpose of the primary key is to provide access to an individual row within the table. Although you can create a table without a primary key, it is usually a bad idea to not have a primary key. A primary key can be made up of one or more columns. A primary key that has more than one column is called a composite primary key. The maximum number of columns is database specific, so you need to check the documentation for your database management system to find out how many columns can be included in a composite primary key. In actual practice, most tables are designed so that there is only one column that is designated as the primary key. When you designate a column as a primary key, it is assigned the not null attribute. That means that when a row is inserted or updated, the column must have a value. If the primary key has only one column, the unique attribute is applied to the column. For a composite primary key, the columns do not have to have the unique attribute, but the value of the composite key, meaning all of the column values together, must be unique. As shown on this slide, you can specify the column or columns to use as the primary key in MySQL Workbench. On this slide, we are looking at the Table Design panel. In the Advisor table, the Advisor ID column is designated as the primary key. The data type is specified as a tiny int of length 3. The tiny int value is also specified as unsigned, meaning that only values from 0 to 255 are allowed. In some cases, the primary key column is a column that has some meaning. For example, in the country table in the world schema, the country code column is the primary key. That means that the three-letter country code is used as the primary key. The assumption is that no two countries will have the same country code, so the country code column can be used to uniquely identify a specific row. When you use a where clause and you specify the primary key and a value, or if it is a composite primary key and you specify values for all of the composite columns, you will get back only one row. A primary key is especially useful when you need to run an update or delete statement. When the full primary key is specified in the where clause, you are guaranteed to only update or delete one row. If you have a primary key that is composed of more than one column, you need to specify a value for all of the columns that are used in the primary key if you want to retrieve only one specific row. If you have a primary key made up of 3 columns, but the where clause only specifies values for 2 of those columns, you might retrieve more than one row. In many tables, the primary key column is a numeric column. The value for the column can be configured as an auto-increment value. That means that when a row is inserted into a table, the database supplies the value for the column, which will be a unique number within that table. In this example, the row ID column is designated as the primary key. It is assigned the auto-increment attribute. In Workbench, check the AI box in the column definition grid. The auto-increment checkbox in the bottom right section of the panel is sometimes disabled. When you check the AI checkbox in the grid, the auto-increment checkbox will also be checked. When rows are inserted into this table, the next number in sequence is assigned to the row ID. The database itself takes care of assigning the unique value for the primary key. Now we're going to look at another type of key that can be defined for a table, the foreign key. Unlike a primary key, a table can contain more than one foreign key. The main point about foreign keys is they are used to relate a column in one table, referred to as the parent table, to a column in another table, referred to as a child table. Foreign keys are used to enforce referential integrity, or RI, within a database. RI is such a fundamental concept that it is one of the main features that sets a relational database apart from other types of databases. One of the main uses of foreign keys is to prevent orphaned data from either being introduced into a database or to prevent changes to the data that would result in orphaned data. In addition to preventing orphaned data, RI can be used to propagate changes from the parent table to a child table or tables. Let's consider an example. In most relational databases, there are sets of tables that are related to each other. For example, you might have a table of customers and a table of orders. When designing that database, a business rule was established stating that for each order in the orders table, there must be a corresponding customer row in the customers table. That implies that one of the columns in the orders table is a column that contains the customer ID. The customer ID in the customers table could be, but does not have to be, the primary key of that table. When you create the orders table, you create a column for the order ID, a column for the customer ID, and whatever other columns are needed for the order. You then create a foreign key that links the orders table customer ID to the customers table customer ID. Now, when you insert a row into the orders table, the database management system ensures that the customer ID of the orders table contains the value that is in the customer table customer ID. In other words, you just can't add an order to the orders table unless there is a corresponding customer. Just as you can't add an order without a customer, the DBMS also prevents changes that would break the relationship. For example, if you try to delete a customer in the customers table, the DBMS will prevent the delete if there are orders for that customer in the orders table. For update operations, you can configure the DBMS to prevent an update to the customer number, or you can cascade the update from the parent table to the child table. RI is a profound feature of a relational database management system. Prior to RI, applications had to be written to enforce RI-like concepts within the application code. There was nothing to prevent code from changing the data and putting the database into an inconsistent state, meaning that there could be orphaned data. That being said, setting up RI is not free. Each column in the parent table that is to be used in a foreign key must be indexed, which I will talk about in a few minutes. It can be difficult to introduce RI into an existing database when there is data already in the tables. The problem is that the existing data might not meet the requirements that RI will impose on the data, so trying to set up the foreign key will fail. When that happens, you usually need to perform data cleansing operations on the existing data so that it will conform to the RI requirements. So let's look at how you can view and work with foreign keys for a table using MySQL Workbench. Look first at the figure on the left of this slide. In the figure, the world schema is expanded and the city table is expanded. One of the items listed under the table is foreign keys. When you expand that, you see that there is already one foreign key defined for the city table. The name of that foreign key is City IBFK 1. One thing you need to keep in mind with foreign keys is that when you define a foreign key, the name that you assign to it must be unique within the schema. That means that two tables within the same schema cannot have a foreign key that is named the same. Now you would think that you could right-click on the foreign key item and get a pop-up menu of things that you can do with foreign keys. But Workbench seems to have a bug. When I right-click on the foreign keys item, the pop-up shows the Create Schema and Refresh All items. I definitely do not want to create another schema at this point. But all is not lost. Still in the Navigator section of Workbench, click on the table name that you want to work with, then click the Table Tool icon as shown in the figure on the right. The Table Tool icon is the icon in the middle of the three icons. To create a new foreign key, click into the Foreign Key Name column and enter the new name. In this example, the new name is City IBFK 2. After entering the name, tab to the Reference Table column. That column is a drop-down list. It will let you select one of the tables that are in the schema. Next, tab over to the column. Here you select the column in the child table. In our example, the child table is the city table, so we are seeing the columns that are in that table. After selecting the child table column, the reference column expands into a drop-down list. It shows all of the columns that are in the reference table. You need to select the column that will be used as the foreign key. If the column that you select is not indexed, you will get an error message. You need to create an index over that column before you can use it as a foreign key. I'll talk about indexes in a minute. Assuming that the column is indexed, you need to select a column that is the same or a compatible data type. For example, you can't create a foreign key relationship between a column that is defined as an integer data type in the parent table and a varchar data type in the child table. Now let's take a look at indexes. An index is another type of database object. It is associated with a column or columns in a table. As I told you on the previous slide, a column that will be used as a foreign key must have an index built over it, so that is one use for indexes. An index can be used to constrain the values that can be assigned to a column. Constrain means to enforce a limitation. For example, we can create an index over a column and indicate that the index is to enforce a unique key constraint. That means that none of the rows in that table can have a duplicate value in that column. If you think about it, that is a valuable feature for the DBMS to provide. For example, if you have a customers table, it would be a big problem if you could assign the same customer number to two different rows in the customer table. The problem would be if you need to retrieve a customer's row using the customer number, you would only expect to get back one row. Some database management systems don't refer to this feature as a unique index, but instead refer to it as a unique constraint. Regardless of how it is referred to, the end result is the same. The DBMS enforces a rule on the values that can be contained within the column for which the index or the constraint is defined. What happens if you have a unique index or a unique constraint defined for a column and you try to insert a new row that contains a duplicate value? The answer is the DBMS will reject the insert and return an error message. If you are in MySQL Workbench, you will see the error message in Workbench. If you are using the database in an application, for example, in a PHP web page, the error will be returned to the PHP application. It is up to the application programmer to handle the error. In addition to constraints and foreign keys, the DBMS uses index to improve query performance. This is one of the main uses of indexes, and it is very important that you become familiar with this topic if you are responsible for the ongoing maintenance of your database. Now, first off, if all of the tables that you are using in an application are small, meaning there are only a few thousand rows at most, you may never notice any performance problems if you don't have any indexes. With small tables, it is possible that the DBMS can simply read the entire table into memory and perform all of the operations on the in-memory copy. But most production applications have tables that contain many thousands or millions of rows. When you start to work with tables that are large, you need to start looking into indexes. When you run a query, there are two primary goals. First, the query must return the correct results. Second, assuming that the query is properly written and you are getting correct results, the query must produce the correct results in the least amount of time possible. Now, there may be two or more ways to construct a query to get the same correct results. So first off, you need to find out which of the possibilities is the best performance-wise. For example, if you have an application that needs to get customer data for a customer, order header data for the customer's orders, and order detail data for each of the orders, it may be better to create a single multi-table join query rather than run 3 separate queries from the application. Once you have the best query figured out, then you look at the where clause and the join on clauses. Let's say you are working with the two tables shown here, a customer table, and an orders table. In your application, you want to return all orders for a customer. So in the select statement, there is a where clause that specifies the customer ID in the customers table. That is the upper table on this slide. We've designated the customer ID column as the primary key for the table. By making that column the primary key, it is now an indexed column. It also has the column constraints of unique and not null. So any new customers that we add to the table must have a non-null customer ID value that is not already in the table. The orders table is the lower table. Its primary key is the order ID, so we will have a unique orders number in this table. To relate the orders table to the customers table, we put a customer ID column into the orders table. We associate this to the customers table by setting up a foreign key relationship between the customer ID column in the customers table and the customer ID column in the orders table. Now the issue is, the customer ID in the customers table is required to be unique and indexed because that column is used as a foreign key in the orders table. But there is no requirement that the customer ID column in the orders table be unique or indexed. You can see that it is not unique. It is entirely possible for a customer to have more than one order in the orders table. So right away we know that we can have duplicate customer ID values in the orders table. Now let's say that we set up these tables and are using them in our application. Over time we start to get thousands of orders. As we keep getting more orders, we start to notice that the application is performing more slowly. Why would that happen? Go back to the query that the application is using. It is a select statement with a where clause that gets a specific customer from the customers table. The select statement also uses a join on clause. That joins the customer table to the orders table on the customer ID column values in both tables. Because there is no index on the customer ID column in the orders table, each time the query runs, the join on has to go through all of the rows in the orders table to retrieve the orders for the selected customer. As shown in this example, the rows in the orders table are not in order by the customer ID column. So even if we have found some orders for a customer ID in the orders table, we still have to go through all the rows. There might be some more orders for that customer later in the table. When you run a query and it has to read all of the rows in a table, that is what's called a table scan. As I mentioned earlier, a table scan of only a few hundred or a few thousand rows is usually not a big deal. But a table scan of hundreds or thousands or millions of rows will have a detrimental impact on how well the query performs. So let's create an index over the customer ID column in the orders table. The name of the index will be IX orders customer ID. The index name must be unique within the schema. As shown in the bottom right corner, the contents of the index are an ordered list of the column values. In this case, the index contains customer ID values in ascending order. Now, just having a list of customer ID values in ascending order is not that useful, but in addition to having the list, the index also points back to the specific rows in the orders table that are associated with each index entry. The DBMS manages the actual pointing back to the rows. Part of what the DBMS manages is to keep track of any changes to the orders table, such as inserts and deletes, and keeping the index entries up to date. Now, when we run the query, the DBMS knows that there is an index for the customer ID column in the orders table. So when it runs the join on part of the query, it does not need to do a table scan of the orders table. Instead, it goes to the index and locates the first entry for the customer ID with the value of 1001. Once it finds the first value for customer ID 1001 in the index, it can simply read the next index value since the index values are in order. Once it hits a value that is not 1001, the join is done. This process of using an index for a table is similar to how you would use an index in a book. If you need to find a particular topic in a book, you can go to its index and find all of the pages in the book where the topic is referenced. If you didn't have an index, you would have to scan through the book, which is like a table scan. Now, it's not all sweetness and light in terms of setting up indexes in a database. When you create an index for a table, you are creating another database object that the DBMS has to maintain. For indexes, the maintenance that is involved requires that when you make a change to the table, the DBMS has to make a corresponding change for all of the affected indexes for that table. By affected indexes, I mean that if you make a change to a column in the table, and there is an index that is built over that column, then the index has to be changed also. The change might be an insert of a new row, in which case a new index entry must be added. If the change is an update, the index will have to be updated. If the change is a delete, the corresponding index entry will have to be deleted. If there are only a few indexes on a table, the ongoing index maintenance might not have a noticeable impact on performance. But if you have a table that has dozens of indexes built over it, and if the table is highly volatile, meaning that there are a great many changes made within a short period of time, then index maintenance can become an issue. Chances are if you have a table that has a lot of indexes, not all of the indexes are needed all of the time. For example, if you have end-of-day or month-end processes that need particular indexes, you may be able to delete the indexes and recreate them just before they are needed. You could save the SQL statements needed to create the indexes in a script file and run that script as part of the process when they are needed. All that being said, if an index is needed for performance, it is almost always better to have the index. Without an index, you will probably end up with a table scan. If a table scan occurs frequently in your applications, you'll probably find that the burden of having too many indexes is better than having the terrible performance without the indexes. You can define an index for a table in MySQL Workbench. Start at the Schema Navigator as shown on the left side of this slide. Under the table name, you'll see an item for indexes. When you expand that item, you'll see the existing indexes for the table if there are any. Click the table name and select the Table Tool icon. I talked about that earlier in this video. It is the middle of the three icons that appear to the right of the table name when you click the table name. On the Editor panel, select the Indexes tab. On that panel, you'll see the existing indexes. You can click into the Index Name column and type the name of the new index. Keep in mind the index name that you assign must be unique within the schema. That being said, in MySQL, you'll probably see that most of the tables will have an index named primary. That index name was generated by MySQL when you defined the primary key column. That name is not considered to be a duplicate index name. Once you enter the index name, you select the index type. The index type is a drop-down list. The two types that you will usually work with are index and unique. Index creates an index, and unique creates an index with a unique constraint, meaning that there can't be any duplicate values in the column. The index column section is used to select the column or columns that are to be included in the index. Although an index can be made of more than one column, you will need to analyze the table and your application requirements before you create a multiple column index. In the next video, we'll look at the basics of database design.